In this clip, we're going to look at partitions and equivalence relations. So this is another topic from your set theory or methods of proof course. So just as a quick reminder, a partition on a set X is a disjoint family of non-empty sets whose union is all of X, right? And so you might have something in mind like saying, okay, if this is the set X, then a partition of it would be something like this. So here are the subsets of our partition. I'm just splitting it up into a bunch of non-overlapping, non-empty pieces. And then if I union all the AIs back together again, I get X. So that's the idea. However, often the sets are not so geometrically pretty. So here's two examples. So for the first one, we'll look at just the integers. And I'll take a set u sub x. This is going to be x plus 2k, where k is in the integers. So for example, u0, this is going to be the set of integers that have been multiplied by 2. So all those guys. And then since it's the integers that have been multiplied by 2, it's often also commonly denoted like this, 2 times the integers. And u1, so this is going to be 2 times an integer plus 1. And so these numbers look like this. And this is also commonly denoted 2z plus 1. And so this forms a partition. You can clearly see all the integers are there somewhere on one of those two lists. And it's definitely clear that z itself is the union of these two sets. The other example we'll look at is if we take the real line and we take u sub theta to be 2 pi times an integer plus theta. So theta plus any integer multiple of 2 pi. And so let's see, so these guys look something like this. Let's see, here's 0. Then maybe if this is my x right here, then I might have over here there's x plus 2 pi, and over here there's x minus 2 pi, and over here there's x minus 4 pi, and so on and so forth, right? So the set that I'm interested in is the all of the green. Okay, and then you can see that the entire real line can be written as a disjoint union, where we take the union over all thetas in the interval from 0 to 2 pi of these sets, and that'll collect all real numbers. Okay, so there's two examples to keep in mind as we look now at the next thing, which is sort of an alternative way of understanding the idea, which is, oops, not an example. And this is the notion of equivalence relation. So so an equivalence relation is a relation which, and I will denote it with this little tilde here on our set X, which satisfies the following properties. It needs to be reflexive. So in other words, it needs to be the case that for every element of our set, x is in the relation to itself. So something like equals, well, x is always equal to x, so that would work. Something like strictly less than would not satisfy this because x is not strictly less than x in any context ever. So it needs to be reflexive. It also needs to be symmetric. So this is for any two elements. If x is in the relation to y, then it also has to be the case that y is in the relation to x. And the third one, which is the most fun, which is transitivity. So the relation is transitive if and only if, whenever you have three elements now, if x is in the relation to y and y is in the relation to z, then it must imply that x is in the relation to z. And so the relation equals satisfies all of this, and equivalence relation is in fact a generalization of the notion of equals. Okay, so if we go back to those two examples that we were looking at, so let's go back to z, which we had just a moment ago, and suppose I consider the equivalence relation where I say two things are equivalent if and only if their difference is in u0. Okay, well, after staring at that for a moment, you see that that's what that really means is that if I take x minus y and I divide it by 2, then I have remainder 0, right? So in other words, it looks like, sorry, when I say it, I mean x minus y, looks like 2 times an integer. Okay, and so this is often written x is congruent modulo 2 to y. Or if you like, x minus y is congruent modulo 2 to 0. Same thing. And so what this means now is that x is congruent to y modulo 2. That means that they have the same parity. So they're both even or they're both odd. If they're both even, then their difference will be an even number. If they're both odd, then their difference will be an even number. And let's look also at R. So in R, we have, let's put a relation saying that theta and phi are equivalent if and only if theta minus phi is in u0. And so this is equivalent to saying that if I take theta minus phi and I divide it by 2, then I get remainder 0, just like we saw before. So that means theta minus phi is equal to 2 pi times an integer, right? And so this is one you've used many times before in calculus. It just means that theta and phi are the same direction. So when you're doing polar coordinates. Yeah? Okay. So those are two helpful examples to keep in mind. Now, of course, so Z is not a vector space, right? But the idea will still come across the same way. And the last thing I want to say about equivalence relations and partitions is that there's a relationship between them. And that is that every partition on X corresponds to an equivalence relation. And vice versa. So given an equivalence relation, you can use it to define a partition. And given a partition, you can use it to define an equivalence relation. And I'm not going to go through the details because this clip is already long enough as it is. But the basic idea is that two elements are equivalent if and only if they are both in the same element of the partition. And since the elements of the partition are actually sets, that's just sort of a horrible thing to say. So I'm going to amend that and say the same partitioning set.